Students, welcome back for this class. Today is our last class for these topics of the chapters which we will discuss about Young's modulus. There are different types of the modulus which are used to calculate different types of the physical quantities. In case of solid, and the most famous law is the Young's modulus, which is the relation between stress and strain. So this law is playing very much effective and vital role in case of engineering, in case of other types of research in the field of science and the physics. This law is basically called Young's modulus. The ratio of stress to the tensile strain, that is called Young's modulus. Its symbol is generally represented by y is equal to y. Mathematically, Young's modulus y is equal to stress. Stress is defined as take right there. Stress is defined by force per unit area, that is the stress. And after application of the stress, if there is a change in length per unit length of any object, like you have done in case of a spring, you have used slotted weights, and after application hanging of this slotted weights, there was increase in length, there was change in length. Initially, you have calculated the length. That was basically strain produced. So strain is in the sense of length, so that's why it is called tensile strain. For stress is the force which you have applied on the spring, and after application of the force, what the changes in length you have observed. This is the ratio between the two, and this is basically called Young's modulus. It is basically force per unit area divided by stress divided by the strain. If you simplify it by using some mathematical relation, that will be y is equal to FL, that is the original length, divided by area on which you have applied the force into the change in length. If you are given the original length of any solid or any object, and you are given up to which area you are applying a force, how much force, and how much extension is produced, then you will be able to calculate Young's modulus. So its unit is Newton per meter square. From where you are getting, look, length of, here it is change in length, unit is meter. Here its original length, its unit is meter. This meter is cancelled with the other meter length. So the only remaining units are force divided by area. Unit of force is Newton, unit of area is meter square. So that's why the unit of Young modulus is Newton per meter square, because the rest units are cancelled with each other. So this is the simplest technique which you use to find out the final unit of any physical quantity. As a unit of Young's modulus is Newton per meter square. The nature of the quantity, it's a scalar quantity. Then consider a solid rod of cross-sectional area A, and length of that rod is L naught. A force F acts on it, which stretches it, lets del L be the change in length. The rod, then change in length is calculated by this. How much length you have increased and from where you have increased. That will be the increase or the change in length after application of the force. So this is del L. If you look at, since the stress is equal to force per unit area F divided by A, and strain is change in length, this one change in length divided by original length, and it is del L divided by L. You put the values in the Young's modulus. This is basically stress, and stress is calculated by using this formula. And if you look at the strain, strain is calculated by using this formula, del L over L naught. So if you put all values in this equation, you are getting this one. Y is equal to FL naught divided by A del L. So this is basically formula to calculate Young's modulus. The value of Y is different for different materials. It is different for steel. It is different for gold. It's different for iron. It's different for different types of the metallic substances. It depends upon the nature of the material. If the direction of the force applied is reversed, then the rod will be compressed. The length of the rod is now decreased by an amount del L equal to the elongation produced in the previous case. Therefore, Young's modulus in both the cases will be the same. So you have to calculate Young's modulus. You need amount of stress applied on any body or object, and then you need to understand or calculate, or if you're not given, you are asked to calculate the strength produced by using this formula, you can calculate the strength produced in the body. If any at any time, if you're given the Young's modulus in the case when the stress of this amount is applied and how much strain was produced, you can calculate by using a simpler mathematical formula by putting the values in this equation. If you look at, this is the length of any rod or any object, solid object. You have applied a force and you have stretched it up to this. So this is the portion through which you have elongated it. This one, this is basically del L, and L is the total length up to which you have stretched it. How will you calculate L, increase in length, minus or subtracting the original length? That will be the in change in length, either in increasing length. So basically, this is the technique to calculate the increase in length per unit length. So the Young's modulus is applicable only in case of the solids only, but it is not applicable. You can't apply in the case of gas or liquids. But if you are asked to find out the relation of stress and strain in case of solids, then you use Young's modulus to calculate the ratio between the two. At the end, you get the value of Young modulus, and this Young's modulus shows what will be the ratio between stress and strain when you are applying at different types of the materials. Either you are applying in gold, then you are applying on silver, when you are applying on any other types of the metal object, what type of the stress will be you have applied, and after application of the stress, what type of the strain you have produced. Basically, this is the ratio between stress and strain. So stress is basically the force directly you apply on any solid, and the strain is the deformation produced if you are applying a force on any object, and deformation produced in length. So that's why these types of strain are called tensile strain. You calculate the ratio between the two, and Y, capital Y, is used to represent Young's modulus. So this was the concept of Young's modulus. Stress ratio between stress to tensile strain. It is represented by Y. Mathematically, it is written as stress divided by strain. Formula for stress is F over A. Strain, it is del over L naught. If you simplify, you get this formula for Young's modulus. Then you have written the unit of this Young's modulus, that is Newton per meter square. Then you said, what's the nature of this? Because there is no direction in which you are stretching it. You are not imposing the direction. So that's why it's a scalar quantity. Then you have considered a case where you are applying a force and you are stretching up to del L, and you calculate the Young's modulus by using this formula. And at the end, for numerical cases, you can easily now apply to calculate Young's modulus. Force is given, original length of the rod or object is given on which you are applying force, up on which type of the area, and how much extension you have produced after application of the force. You can calculate. If Young modulus of that substance is given, and you are told that certain amount of Newton force is applied on an area of certain area on a certain length of rod. So what will be the extension produced del L after putting the values in this equation? You will be able to calculate the extension of the change in length produced in the solid. With this chapter ends, and also this class ends. I hope you people have understood all the topics from this chapter, starting from properties of the matter and ending up with the Young's modulus. Thank you very much for your patience.